Welcome to Examalist. So we are continuing our discussion on rotational motion. Okay, so from the last class, we understood that if you have a massless string of length r and you have a particular object of mass m present at length r, then the moment of inertia I is equals to mass m multiplied by square of the distance where the mass is concentrated. Remember that this formula is valid for an object that is attached at a distance r from the center. However, if you have a rod, so consider this is a rod, okay, and if this rod is attached to a particular point O, okay, and this rod has a mass m, then the moment of inertia of this rod is not m r square, okay, because the entire mass is not concentrated at any distance r. So what is r? So r is the length of the rod. Okay, so please understand that for the rod the entire mass m is not concentrated. Then how to find the moment of inertia of rod, that we will discuss later on in the next lecture. But now we have something to discuss, that is I equals to mr square becomes the moment of inertia for this system. What is the system? A single mass of mass m attached at a distance r from the axis of rotation. O is the axis of rotation. Great. So what I want to discuss here is that in translational 1D motion we have this formula where force can be written as the rate of change of momentum. Okay. Now the question is, since in rotation torque plays the role of force, I mean torque is the main thing in rotation that is responsible for the rotational effect, not only the force but also where it is applied. That's why we use torque. So question is, can we write torque as the rate of change of some quantity? Now question is, what will be this quantity? Agreed? Let us see. Okay, so for this object where a mass m is attached at a distance r, okay, now consider this object starts rotating with a velocity v. So if I have shown a velocity v, it means how is the object is moving? The object will move in a circular path. Okay, keep that in mind. The object will move in a circular path, and at each point, since the object, as I've said, the object is moving at a constant velocity v, then each point the tangential to this path will be v, because the object is moving at a constant velocity v. Now, so can you tell me what is the momentum of the object? Of course, the momentum of the object is mass into velocity. Of course, the momentum of the object is mass into velocity. But there is one interesting thing. One interesting thing is that you know one thing, that can you tell me if this string of length r starts moving at a particular omega, okay, so if omega is constant, then the velocity is also constant, I mean the velocity at the edge. So if this velocity is v, then can you tell me what will be the velocity somewhere around here? What will be the velocity of the this part of the string which is very much close to the axis of rotation, or O? This part of the velocity will be v dash, and as I discussed earlier that v dash is always less than v. So what am I coming into? What I want to tell you? So I want to tell you that consider, instead of the mass being here, just keep the length of the string as it is. Okay, the length of the string was r, and if I now keep the object of mass m somewhere around here, if I keep the object of mass m somewhere around here, then at this point, what is the momentum? So the new momentum is now the same mass, but velocity is different, that is v dash. So the new momentum p dash is m into v dash. It means if you shift the distance of the if you shift the mass on the string from one point to another, then the momentum is changing. Now try to think about it. The momentum changes with respect to where you have kept the object. It means that not only the velocity is important, you need to understand that where you keep the mass is also important. Agreed? So to include the importance of r in momentum, we defined a new momentum L called as the angular momentum, and we said that do one thing, just multiply r with the momentum that already you know, with the linear momentum. This is the momentum in rotational motion. So if I remove the cross product, remember cross product is always written for general case. So there can be cases where we can have sine theta as 1 when theta is 90 degrees. So we are not concerned with cross product more. I can write r. What is momentum? Momentum is mass into velocity. So now for this object of mass m, I can define a new quantity, and that new quantity is called as the angular momentum. Okay, and angular momentum is defined as mass of the object multiplied with the velocity with which it is moving and multiplied with the distance from the center, distance from O. Now if you look at this interesting quantity, then you will learn something very important. So if you do dl by dt, just dl by dt, agreed? So what will happen? So what will happen is, by cross product rule, okay, you can have a term dr by dt cross p, and the another thing will be r cross dp by dt. This is pure mathematics that we are doing. Okay, now this part is 0 actually. This part will be 0. Why? So what is dr by dt? You know dr by dt is velocity. So velocity cross, what is momentum? Momentum is mass into velocity. So mass is a scalar, it will go outside. So you will have velocity cross velocity. So we know that cross product of two same vector is 0. So this part will have no contribution because it goes to 0. So what are we left with? We are left with dl divided by dt equals r vector. So what is dp by dt? dp by dt is force. Amazing, right? So you got the torque. So you can say that torque is actually rate of change of what? Like force was rate of change of momentum, torque is rate of change of angular momentum L. Agreed? So understood this part? So the reason we defined a term called as the angular momentum, because angular momentum is the quantity whose rate of change of gives you torque. Okay. So let me okay, remember this one, let me write in I alpha just for completeness of this part. Okay. Anyways, so torque is rate of change of angular momentum. I think this part is clear. Now we'll talk about little bit of energy. So why there is something called as rotational kinetic energy even though we have our kinetic energy. So in translational motion, you define something called as kinetic energy, and if an object is moving at a particular velocity v, then you say that the energy of the moving object is half mv square. Interestingly, there is only one mass which is moving at a velocity v on a 1D road. Agreed? Now question is, what is the analogous energy in rotational motion? Again, let us study our system. So what is our system? You see, we are considering a very easy system where the entire mass is concentrated at a particular distance r. This system is very easy for us. If we have a continuous system, then we have to actually find the, we'll do it. Let us find the energy of this system. Okay, now if this object starts moving with a velocity v, then what will happen? Then this ball will trace a circle and it will move with a velocity v along the circle. Agreed? So what is the kinetic energy? Obviously you will say that kinetic energy is half into m into v square. Agreed? But you would say, hey look, v is a function of r, okay, and we know that omega is constant, so why not write it in terms of omega? It will be better. So you know that this will be half m. So what is v? V is r omega, so you'll get r square omega square. So what do you get? What is mr square? Mr square is moment of inertia that acts as mass, and this one acts as a velocity. Now question is, when this is so good, then why we have written this? There is an interesting reason behind it. You see, in rotational motion, omega is the main thing that is constant. V is not constant for rotation because v is a function of r. If you look at, if you place this mass, okay, instead of putting the mass here, if you place this mass somewhere around here, then the kinetic energy will be different. Okay, so let me tell you how it is different. Okay, now consider the same diagram here. Okay, now what you do is, now you just place another object somewhere around here, and let this object has this object is at a distance r dash, and the velocity of this object is v dash. Now if I ask you what is the kinetic energy of this system, what would you say? You would say that we have to add the kinetic energy of both the path. So the kinetic energy of first ball is half m is the mass of the second green ball. So let me write in their color. Okay, that would be better. So the green ball will have energy how much? Half. Since the mass is same, so m, but what is the velocity? V dash square. Now what is the kinetic energy of the red ball? The kinetic energy of the red ball will be half m v square. So an interesting thing is, since v dash and v is different, so I am facing a bit problem to reduce this big equation. But this big equation will be reduced if I just introduce omega. Why? So what will be v dash? You know that v dash will be r dash into omega because omega is constant, and even v will be r into omega. So let us see what happens when we introduce this omega. We know that omega is same for all the ball, whether you are near or you are far, omega is same. So this will be half m. So what is v dash? V dash is r dash square into omega. And then what will be the kinetic energy of second ball in terms of omega? This will be half, this will be m, we have an r square and an omega square. Now interestingly, this omega is same for both the balls, So what will be the final product? The final will be half. There will be an m r dash square plus there is another ball which is m r square, and there is an omega square. Agreed? Now look at this interesting object. Look at this interesting equation. This interesting equation is speaking something. This interesting equation is begging you to write this as half. So what is m r dash square? M r dash square is the moment of inertia of the green ball. So let me write it as I dash. And m r square, say, is the moment of inertia of the other ball. So let me write it as I. And then this is what? Omega square. So what is I plus I dash? I plus I dash is the total moment of inertia of the system into omega square. So the reason for introducing omega square is because the moment of inertia can be directly added. And remember, moment of inertia acts like the mass in translational motion. So what do you understand from this? You understand that kinetic energy is same. Kinetic energy is half into mass into velocity of the object square. So kinetic energy is same. The moment you introduce omega, the r square term comes out, and when the r square term multiplies with the mass, you get a moment of inertia. Now the entire moment of inertia gets added and you get a omega square. Now you would ask a question, why the hell we need this? The reason we need this is the following. If I now give you the question where I have kept 3 balls. So this is ball number 2, which is at a position r dash, and there is a ball number 3 which is at a position r double dash. If I now ask you what is the kinetic energy, what you will do? You will say, okay, we need to add the energy of all the 3 balls. So first energy of the ball is half mv square. The energy of second ball is half mv dash square. And the energy of third ball, which is the ball closest to the O, is half mv double dash square. But I would say you that, hey, look, I can write this very easily. Don't do this much big equation and then solve it. So let us write directly. The kinetic energy of the system of 3 balls will be half I total into omega square, because you know that omega is going to be same for all the 3 balls. And now you can easily tell me what I total is. What is I of the first ball? It is mass of the first ball into r square. What is I of the second ball? It is mass of the second ball into r dash square. And what is third mass of the third ball into r double dash square into omega square. So easy, right? So the reason we introduced this formula, where the formula says that if you need to find the kinetic energy of a rotating system, add the moment of inertia, and since omega is constant, square it. The reason we invented this formula by using so much difficult equation and derivation is because we can write the total kinetic energy very easily by just adding the moment of inertia. We don't have to do this and then hundreds of conversion of this to r omega. This is r dash omega, this is r double dash omega, and then take all the omega square common, and then you have the same thing. Anyhow, you will have this thing. So the reason we invented the I moment of inertia is because to tell you that whenever you are dealing with rotational motion, all you need to find is the total moment of inertia, and total moment of inertia is just addition of the individual moment of inertia of various part of the system. And when you add all the individual momenta, you get the total momenta, and then the kinetic energy is half total momenta into omega square. So this helps you to ease your calculation. So whenever you are given a system, all you need to do is find the total momenta. So in the next lecture, we'll look at, so this is a system, this is a system of 3 balls. If I now put infinite amount of balls, what will happen? If I put, instead of this, if I put infinite amount of ball here, 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 what will happen? I'll get a rod. So a system of infinite amount of ball is equivalent to a rod. Now question is how to calculate the moment of inertia of this rod. We'll discuss it in the next lecture.